Okay, so we've successfully gotten through the week one problem. And there was a little bit of confusion there because I think Al Frazier had put in sort of a what if we were running that motor at a full 70 kilowatts, which is, right on the order of that 100 horsepower. And in that case, the demand factor would go up because we're actually running at a higher energy consumption rate. So just to recap problem one, which we did in the previous lecture, the service fee is straightforward. It's just your monthly times 12. Your energy cost is also relatively straightforward, and that is the energy, which is power times time. And again, we're running for 2,600 hours a year, 10 hours a week, 52 hours. 10 hours a day, 52 hours a week. And then there's our load factor, which comes in. And then finally, to calculate the demand cost, we're multiplying the power times the demand rate on a monthly basis. Okay, so that's all for problem uno. Whew. All right, this is Bowers from last year. File. Problem two. Okay, I guess Bowers. Yeah, this is actually a pretty nice job. Yeah. Okay, let's dig into problem two now. Problem two. Let me just double check. And what I'm asking you all to do that's fine. So there are other outstanding questions that are pertinent. Okay, here's just double check. Good. Okay, everybody's happy. Okay. Bear with me here, I'm just making sure I didn't miss anything. Okay. Okay, I think we can answer that. Finally, Warner. Okay. All right, looks like we're in good shape. Guys, good discussion there. I'm glad you're working that out. So let's finally get into problem two. Read the assignment. Okay, problem two says, calculate the annual electric costs for each air compressor using the provided data. This compressor comparison helps illustrate the concept of utility demand. This is a real situation where you could run a 100 horsepower or a 150. Both are running to meet the same requirement. Okay, so they're both going to run at, well, we're assuming that 8760 hours in a year. We're looking at a use factor of 40%. We've got a little bit of data, but we're going to assume this is kind of what happens on a daily basis. We're going to use rolling average to calculate demand. And we'll also see rolling average in resources 4. So the customer has the option to operate either compressor. Both compressors are on the only loads on the same meter. No others would affect it. And use the data. And then again use the same guideline for service. So the numbers have changed just a little bit, but there they are. Okay, so let's go into the problem. Let's go into the solution. All right, so this problem's a little more involved. Okay, let's just look at the summary, because the same the same basic logic that we applied to the 100 horsepower motor applies to the 150.
Right.
Okay, so what we're first looking at is the average kilowatts. This is what we just calculated for the 100. Now let's see where we get the average kilowatts for the 150. So you've got a data set here, and here's the rolling average. So for example, here's minute 36, 37, 38, et cetera, et cetera. This number right here represents 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15 minutes. That's the 15-minute rolling average. So there's that guy. There's the next one. There's the next one. So there's sort of the rolling average of each of these powers. So that's what these guys are, and then let's just take a look at that. Yeah, so same deal. So if we go back to the summary, 34 horsepower, well, 33.6. So you go back to this guy and equals average of the averages, 34.1. Well, close enough, right? Point is, you're going to get something. You're going to get less. It's going to take less horsepower on that 150 because it's just bigger. It's going to be less of the capacity. You're going to pump just as much air, but it'll be less. Okay. Now, energy per year. This is coming from HPB10. Let's see that guy. HPB10. There's that. So here's where it's running at 40%. So there's your total hours per year is 8660, and the motor is going to run is going to run 40% of the time. Now that's about 10 hours a day, 5 days a week, approximately. So the numbers are about the same. we're looking at the average of B20 to B381. That's just the, the average of all of those powers. And again, it's going to come out to be about that 52. So power times time is energy. 180,000 kilowatt hours per year. Demand is the max of all of those. As it turns out, you're right around 52 kilowatts. So for this guy, your energy cost, and again, these are old numbers, but you're multiplying energy times dollars per kilowatt hour. Your demand cost, again, is that power times the price. And then your operating cost is your energy cost plus your demand cost. So to run, and these numbers again are a little wrong because of the previous year's utility rates, but again, $15,529 to run the 100, plus the service fee, 16. Okay, so that's what it costs to run the 100 horsepower, $16,000 a year. Now, it looks like the 150 is less. And you can see we've used the if statement again. So you get the, kind of handy, keeps you from having to think, yeah. I mean, you can screw, as long as you don't screw up your code, it'll tell you. I mean, this basically allows, somebody who, let's just say, someone's sat back and done these calculations for you. It allows the new guy to go out, put in the numbers, and make a decision for him. Basically, is what that's doing. Okay, so let's just see where these numbers come from. Energy cost for the 150 is here, coming from B10, so it should look almost exactly the same. Again, we're taking that 8760 times 40%. Make that a little bit bigger. And again, the 150 is not running as hot. Now let's see, it's taken the max of F34 to F67. It's taken the max of that rolling demand. So energy is kilowatt hours times dollar per kilowatt hour, and the demand cost. And so since the 150 is just not running at as high of an overall power, the demand cost is less. And so in summary, well, the energy cost is less and the demand cost is less, so you use the 150. That's it. You can say, well, by making that decision, you just save your company $5,000 a year. Let's go on vacation.
That'd be one heck of a vacation, $5,000. Could be.
Could be a good one. A couple tickets to Paris. Yeah.
I really don't Mexico.
Down to Mexico. Okay.
It's beautiful out there.
Is that it?
It for today.
That's it.